Good afternoon, ladies and gentlemen. It's a great pleasure to be here. Wonderful atmosphere, wonderful audience. I'll try in the next 18 minutes to give an answer to this question. Could the sun be responsible for global climate change? It's a question I started thinking about almost 30 years ago. At that time, it was already clear that the world is warming. It's much clearer now. At that time, already most scientists were quite sure that it was due to man-made greenhouse gases. But there was a small and very vocal group of people who said, no, it's the sun. So let's look at that. And now, nearly 30 years later, I think we have a good answer. And I will try to give this according to the knowledge we have now, right? This is science. Things change. Let's start with the climate. What you see in the diagram shown here is global temperature, averaged over the whole Earth. And each color bar, vertical color bar, is the temperature averaged over a whole year. The ones which are blue are below some average temperature. The red ones are clearly above that. And if you look at this diagram, you'll see that before about 1980, most of them are in the blue. After that, all of them are in the red. At the same time, we have also been measuring carbon dioxide. That's the main man-made greenhouse gas and its concentration in the atmosphere, and that is shown in this upper diagram, the red curve. It covers a longer period of time, so I've put a frame around it so that you have exactly the same period of time within that frame as for the lower diagram. And if you compare the red curve in the upper diagram with the thick black one in the lower one, the thick black one is just a running mean, they do show some similarity. Okay, let's leave it at that and move on to the sun. There are many fascinating things about the sun, but the most striking feature, if you look up at it, is just its sheer brightness. Right? It's 150 million kilometers away and still incredibly bright. Don't look into it, okay? It's not good for your eyes. If you take the total brightness, the total energy that the sun is sending out every second, it's a whopping 10 to the 26 watts. That's one with 26 zeros after it, unimaginably big. I can't imagine it either. Where does the sun get that energy? It has to replenish it somehow. And it comes from nuclear reactions in the core of the sun, which has a temperature of 15 million degrees and a high density. And at that temperature and density, the lightest element, hydrogen, the atoms of hydrogen diffuse together, form helium, and release a lot of energy. This is exactly the same process that takes place in a hydrogen bomb, right, which is the mightiest explosion humans have been able to produce, except that in the case of the sun, it's not one hydrogen bomb, it's billions of them going off every second. Don't worry, it's quite stable. The sun's been doing that for 4.5 billion years, and it'll continue to do that for another 4.5 or more billion years, and we'll be quite safe. Most of that energy just goes off into space in all directions. A tiny, tiny fraction comes to the Earth. But for the Earth, that's basically all the energy that comes. So if you look at the surface of the Earth, the atmosphere, more than 99.96% of the energy reaching there is coming from the sun. What happens with sunlight, with the radiation that is reaching Earth? On the upper left, the sun, on the lower right, the Earth. The yellow arrow shows the input, the light coming from the sun. A part of it is just reflected by clouds, on the sea, ground, wherever. A part of it, however, is absorbed and taken up by the Earth and warms it. It is then re-emitted, but not in the visible, but rather in the infrared. because the Earth's temperature is much lower than that of the sun, so the natural radiation for the Earth is not invisible, but it's warmth, right? And this infrared radiation, if there is no greenhouse gas in the Earth's atmosphere, will also just escape into space, and you will get a certain equilibrium temperature for the Earth. If, however, you do have greenhouse gases, like carbon dioxide, in the atmosphere, then these molecules will absorb part or all of this infrared radiation coming from the Earth, and they will re-emit it again, but in all directions. So a part of that will still go into space, but a part of it will come back down to Earth and will cause more heating. So the more greenhouse gases, the warmer the Earth you get. Okay, a warm Earth. We need it, don't we? I mean, this hugely diverse and incredibly beautiful life forms we have here on Earth, they all require energy. They're all living from the sun's energy. So, if you were to switch off the sun, if there were no sunlight, we would certainly not have any higher forms of life, not on the surface of the Earth, not in the atmosphere. Now, if the sun is that important for keeping the Earth going, couldn't just some small changes in the sun totally change our climate? It's a reasonable question to ask, right? So, could the sun cause climate change? Only if it is variable, if the sun itself changes. Does it? Yes, it does. The image you see here is the sun seen in X-rays. Each image is taken 1 year apart, and if you start at the bottom left, you see the sun is pretty bright in X-rays. That was a time when it was very active. If you go now 5-6 years towards the top, you reach a time when the sun was not active, and it showed almost no X-rays. It changes in brightness by a factor of 100 in X-rays. You wait another 4 or 5 years, and it's back again. It's active again. And this keeps going. The sun has a so-called activity cycle. Every 11 years, it picks up, becomes more active, down, up, down. X-rays is one example. A more famous example, and one where we have much longer running observations, are sunspots. Sunspots are dark features on the surface of the sun. You see on the little image at the top, the solar disk, as seen in white light, as you would see with a small telescope, and there's a blow-up of some of the sunspots there. This was a time when there were quite a few sunspots. This is a time when there were very few or none. The first, when the sun was active, the second, when it was inactive. In the image below, you see the number of sunspots as they go up and down, up and down, up and down for the last 400 years. And you see all these cycles coming, going, very regular. But there was also a time between around 16-something and 1700 when the sun had almost no sunspots. Now, if by chance or not, that was also a period where it was extremely cold, especially in Europe and the North Atlantic region, the Little Ice Age. Not the real Ice Age, but the Little Ice Age. A time when lakes froze, people went skating, the Flemish masters painted beautiful pictures of that. I spent some time in Holland, it never froze. There was another period of time, around 1800, the so-called Dalton minimum. Again, the sun was not very active, very few sunspots. Again, it was very cold. This could all just be by chance, right? This doesn't mean, because why would sunspots actually produce climate change? Wouldn't the brightness of the sun as a whole have to change? And so we can check. Yes, since about 40 plus years, we can measure the brightness of the sun very, very exactly from space. And this is the total data that we have. And indeed, you see the brightness goes up and down, again with around this period of around 11 years. The amplitude is small. It's only 0.1%, but it is there. If we compare now with the number of sunspots, they correlate rather well. When you have many sunspots, the sun is actually brighter. Does that mean that during the Maunder minimum, when there were few sunspots, was it darker? Could that be the cause? Well, these are measurements, and this is the total length of the measurements we have. There were no spacecraft flying during the Maunder minimum. Right? We couldn't measure this. So we need something else. We need a model. We need understanding. We need to know what is causing this. And this was something which, together with my group, one of the tasks I've been working on for many years now, especially with Natalie Krivova, we developed the so-called Satyr model. And here, on this diagram, you see again the measured brightness of the sun, which is again in red, and the green dashed line shows the model, our Satyr model. Right? For this period of time, they agree reasonably well, I would say, especially in the recent times when the measurements were really good. Okay, so we have a model we can now compute, and sure enough, we find during the Maunder minimum, the sun was less bright than it is now. Yeah, could that have been it? Maybe, maybe not. Poor statistics, right? You need to have many more such periods when you had few sunspots. And you can't go back much more than 400 years because the telescope was only invented in 1609. But nature is kind to us. It has provided us with an indirect way of finding out what the sun was doing, not just 500 years ago, but 5,000 or 10,000 years ago. And this has got to do, very surprisingly, with cosmic rays. Cosmic rays are nasty little particles coming from deep, deep space. These are protons, most of them charged particles, traveling almost at the speed of light with very high energy, coming and hitting our solar system. Luckily, we have a few shields which help us. One is the sun itself. The sun's magnetic field acts as a shield and keeps many of these guys away from the Earth. The Earth's magnetic field and the Earth's atmosphere also help. But some of them get through. And if one of them reaches the Earth's atmosphere, because they have such high energies, they immediately interact with the molecules that are there. And because they have such high energies, these are nuclear reactions. Totally new particles are produced. And one of those is carbon-14. That's a heavy form of carbon. It's radioactive, and if you find carbon-14, you know it had to be produced this way. No other way. Except in recent years, but for a long time back. Part of this carbon-14 will end up in trees, end up in tree trunks, in the wood, and because woods have these nice lines, they have year rings every year, you will see, if you measure the amount of carbon-14 within such a tree ring, you know how much carbon-14 was produced at that time. And from that, you know how strong the sun's magnetic field was, and that tells you how active the sun was. You have the theory which will put all of this together. You can say how many sunspots there were, etc., etc. Okay, so we have that activity. Let's plot it. Oops. Let's plot it. So here we have plotted versus 12,000 years. 0 is today, 12 is 12,000 years ago, at the end of the last ice age, the real ice age. Carbon-14 production rate, that doesn't really mean anything to you. The only thing you need to know that when the blue curve is pointing up, that the sun was less active. Okay, it had less sunspots, less X-rays, less bright. And now let us compare that. And let me point out that if you look around 0, there is one spike going up. That's the Maunder minimum, but there were also earlier such periods of time. Now let's also plot climate. Again, you don't need to know what exactly is plotted. Arrow pointing up means at the top. If the yellow curve goes up, it was cooler in the North Atlantic European region of the Earth. Not the whole world, but this part, and this is an important part for us because this is where we live. And if you compare these two curves, you'll find that in many places where the blue curve shows up, the yellow curve does too. So, times when the sun was inactive, typically it was cooler. Quite a bit cooler. This is no proof, but it's a suggestion that the sun did play a role in determining climate. It's not the only thing, right? There were also volcanoes, natural variability, etc., but it did play a role in determining climate in prehistoric times, partly in historic times, but the important question is, how about now? This is the time we're living in. This is where we are seeing global climate change to a much larger extent than we have over this diagram over here. What was the effect of the sun? So let's look at this plot. This goes back around 140, 150 years. There are two things plotted here. The first is global temperature. It's basically the same as I showed you right at the beginning with the blue and red bars. The thin red curve is yearly values. The thick one is an 11-year average. The yellow curve is the brightness of the sun. Total energy emitted by the sun towards the Earth. Thin yearly values, thick 11-year averages. The yellow curve has been put together by measurements which were carried out in the last 40 years, as I showed you. There is a bit of uncertainty there because spacecraft and keeping instruments stable is tricky. So we cannot be absolutely sure that the sun was darkening in the last 40 years. It could also have remained roughly stable, but it was somewhere in that triangle. Before that, they use our model, and that reproduces the data relatively well. So if you compare the two, you see that up to around 1970, 1980, yeah, they're sort of running a little bit in parallel. Doesn't mean anything, but the important thing is, after 1980, they are clearly diverging. So even if the sun was responsible for a large fraction of the climate change we have seen through the whole Holocene, it definitely is not the driver now. We have to look at ourselves. It's the man-made greenhouse gases. There's no getting away from that. Thank you very much.